Welcome back. I wanted to do a quick demonstration on how to disassemble the LC575 or any LC or Performa 500 series all-in-one. And it's actually remarkably simple. These are probably one of the easiest machines Apple has ever made to service in terms of the all-in-one variety. I mean, they really are that simple. The first step is you've got to remove the motherboard cover, or the rear cover. Take that off. Slide the motherboard out. It's mounted on rails. It couldn't be easier. Here's the motherboard. Just a single board. That's it. Then, using a T15 Torx driver, there are 5 screws holding the shell on, all around the display here, and around the other side. And there's one on the bottom. And I'll show you where that is. No need to remove the front cover. By the way, the front cover is a pain to remove on these older ones because the plastic is so brittle on the clips that there's a really good chance you could snap them off. So I only remove that cover when I absolutely must do so, and this is not one of those occasions. But if you must remove the cover, slide a butter knife through the slot on the bottom, and then let me rotate it for you so you can see. But what we're going to do here is we want to take the cover off because it still smells like a damp basement. And every time I fire it up, my whole house starts to smell like a damp basement, and I'm getting tired of it. So I'm going to blow all the dust out. But this little slot right here, you want to stick a butter knife in there. And then press downward like that on this tab, and then this whole panel slides down. That's how it comes off. But like I said, the plastic clips are so brittle. I've already broken one. I don't want to break another one, so I'm only taking it off if I have to. I've already gone and removed the screws. Here's the screwdriver that I used. It's nothing fancy. It's just a T15. And then we're going to gently pull up. And the whole cover comes off. Now let's take a look at the anatomy of what's inside. Let's take a look at what we have here. I'm one of the last Apple techs to have ever had to gone through CRT training. And the CRT training modules were done online. It was never done in person, so there's no real practical experience. I kind of had to train myself that part of it. But I know how to properly discharge a CRT. I have the actual Apple tool to do so. I always passed that safety course every time I renewed. But to discharge a CRT, you need a CRT discharge probe. One can be made using a screwdriver, and I think you're supposed to add a resistor somewhere in there so that it doesn't de-energize all at once. It does it slowly, so there's no arcing, or there's very little arcing. And I just wanted to take a moment to show you what the actual proper tool looks like. This is this is Apple's version of the CRT discharge tool. This is the one that they would sell to their service centers and technicians. This is part number 0760381. It has since been discontinued for obvious reasons. It's in its original box, and it comes with the CRT discharge probe, a ground lead, or a ground strap, and some foam. So, this is the actual probe that you would use to discharge. You would slide this needle underneath the anode cup, and of course you would ground this first to chassis ground in that, so in this order you would ground this to the chassis ground, and you would slide this in there, and it would slowly, well, it would fairly quickly discharge the anode completely. There is a resistor inside this this probe. In fact, I will prove it to you. So it has a resistor. They value, total value with the probes and everything included, of, looks like 0.3 ohms. 0.6 ohms, 0.7, 1.3, 1.8. Yeah, there's a resistor in there, I swear to God. Let me try to clean up these. Yeah, it starts off at 0.3, and then it slowly trickles up from there. And the resistor is there, of course, to prevent sudden discharging, which could potentially cause damage to delicate circuitry by unloading that thing so fast, and to prevent massive arcs from startling the technician who happens to be there. That could kind of be not shocking to you, but it would be startling, and you might wind up, doing something stupid like stabbing yourself in the eye with the discharge probe. Now, after you discharge it, you're supposed to take this sucker and ground that anode to the chassis ground to prevent it from recharge or building up a charge and re-energizing itself. I'm not a scientist. I'm not an electrical engineer. I can't explain that phenomenon, but I've heard of it happening. So that's why they give you this device. It is fused with a little glass fuse, and I surmise that it might not be a bad idea that before you use this jumper tool, that you want to make sure the fuse isn't shorted. You can do that, not shorted, did I say that? And make sure the fuse isn't blown. You can do that by using your handy dandy multimeter and putting it on tone check and see if it's any good. It is good. Now, it has 1 ohm of resistance, roughly. So there might be no, there's no resistor there that I can see, unless that fuse is some kind of resistor. But there's a little bit of resistance to this tool somehow. How is that possible? Is there a resistor in there somewhere? No, there is not. That's interesting. Now this looks like an ordinary plain Jane old fuse, so that's pretty cool. Yeah, I thought there'd be like a resistor in here, but there isn't one. Okay, moving along. A really nice fuse holder, nothing else. Alligator thing. And you want to attach the probe to a chassis ground, and I believe a good chassis ground would be this piece of shielding here, or I prefer to use the ground pin myself. And then you stick the probe between the CRT glass envelope and the aperture cup. Once it's discharged, you let it sit there for a couple minutes, I do. Then you want to invert this cup by peeling it back, and then there's a clip. You just squeeze the clip with some needle nose pliers, and this comes off. As of right now, this is probably energized with, I believe when it's up and running, I believe it's somewhere around 30 kV, which is enough to kill you. I won't lie, it's enough to kill you. One of the safety measures that I remember specifically is you never want the jolt going across your heart. So that's why you keep one hand free and you only work with one hand. Because what you don't want is that jolt going through one arm and out the other to the grounding point. Because that will cause, could cause a cardiac arrest situation, as far as I understand. So let's take a look at what we got here. Now this is our microphone lead. This goes up to the center top of the display housing. This is our degaussing coil right here. This is just a copper coil. When it's energized, it produces a magnetic field, and that is to if there's any magnetic exposure or there's any gaussing of the shadow mask. This is designed to neutralize that. And this energizes only for about a second or two. It's not even 2 seconds in some cases, depending on the display. But I believe it's like 1 or 2 seconds. It kicks in. The connector for that is right over here. So there's a relay. I believe it's this relay right there Let me zoom in on that. That relay kicks in for just a second or two, which provides 120 volts directly into this coil, which produces a momentary magnetic field. Alright, what else do we have here? Here's our flyback transformer. This is what generates the high voltage. This is a ring circuit. You can read more about ring circuits online if you wish. So it takes 120 volts and steps it up to 30,000 volts or so. And that's what produces the high amount of current needed to run the display. Now right here we see something called fan connector. When we took the back cover off, we didn't see a cable going to a connector from the cooling fan. And where is the cooling fan? So I'll show you. The cooling fan on this unit is mounted directly to the case, and it interfaces with that connector through two contacts. So if you ever put one of these together after taking it apart, it's a really good idea just to make sure that fan is spinning, to make sure that nothing happened to those contacts during the time you had it apart. That would be a good time to figure that out right there. So what I'm going to do now is I want to blow all this out. It's really disgusting. It smells like an old damp basement, and that bothers me. So I'm going to blow it out with compressed air. So I got to get my air compressor outside, get it charged up, and we'll do some cleaning. All right. Looks like it actually worked. Let me grab the air nozzle. Unfortunately, this has the wrong fitting on it. This is, I forget the name of this. This is not the right fitting at all. So it leaks like a sieve. But it gets the job done. I gotta let it charge up a little more, and then I'll get the back side of the CRT. See this right here? This is like, there's mold growing in there too, so I want to get that out of there. Now the inside of the shell had to be done by hand with a damp cloth. I used a Windex, which I use for damn near everything. So that's all nice and clean. Now take a look at this. Much better than it was. Much better than it was. I mean, it's I mean, it's not like anyone's ever going to see what this looks like inside. I mean, that's just not likely going to happen, but to me, it's all part of a good restoration and preservation effort. You want to clean it as best as you can without damaging anything. I actually found the authorized service manual for this thing, and so here's what these are: left to right, right to left. VS is vertical center. That's this one here. HS is horizontal center. Vertical size is VH, vertical height. And then HW is horizontal. Focus. Focus is actually on the board towards the CRT. It's, there it is. There's my focus. So we're going to play with that one a little bit. Now the other ones are for individual electron gun adjustment. We've got, so there's a utility that you're supposed to run, the CRT adjustment tool that Apple has produced for this machine, and I don't have that tool, and Apple no longer provides it, but I'm sure it's out there somewhere, and I believe it was a bootable CD or something that it would run off of, and you could adjust the display exactly as they would at the factory on a new machine during initial alignment and test. But what we're going to do is we're going to fire it up at full brightness, and we're going to play with the focus. I actually have some CRT alignment tools that I bought. I think I still have them. If I have the right one. Let me slide the board back in. We're going to fire it up on the bench here, or on my desk. So as of right now, this is all energized, absolutely 100%. So we're going to be very careful when working around all this cool stuff. Alright, found the tools. Let's see what we can do about getting the focus a little better. I think we've got that centered as much as we're going to. Absolutely. I don't think I'm going to get it any better. But one of the cool things about this manual is it also covers convergence adjustments. So that means adjusting those little ring magnets on the end of the CRT neck. It covers everything. So you could bring one of these from a fairly non-functioning state to a functioning state using the Apple Service Manual. I mean, look at this. There's so much covered here. They don't do that anymore at all. They don't cover any of that stuff. It's all just replacing parts now. But there we go. Let's put it back together again. Real quick, how long has it been since you remember using a computer that could do nothing else while printing a document? I can't do anything else. I can't do anything. It's until this document is done printing, that's it. These machines were not good for multitasking. I want to point that out. Alright, so here it is. Let me just move my stuff. Okay. So this particular keyboard, what you've got to do is remove 12.5 screws. So this is what they call a membrane keyboard. This is not a buckle spring or a clicky keyboard. This is a membrane keyboard. This is not dissimilar from the keyboards that are made today. And they're very prone to failure. That's one of the downfalls. But they're quiet. And they claim that, I believe when these were becoming a thing, they're not only less expensive to make, but they have a selling feature that they were able to tout, especially to offices and schools. They're silent. They're very quiet. Or the Dell Quiet Key keyboards that were so popular in the 90s, well, that's because they are also membrane keyboards. So you've got a steel plate on the back. Let me, there we go. You got a steel backing plate here. You've got your, this is your pass-through interface. This is where your mouse connects. This is, it just goes right through the main board here. To remove a couple more screws. There's a ground strap. The construction of this keyboard is ridiculously cheap. I will completely level with you guys. It is. I'm almost tempted to go back and just buy another. I think it's the Apple. Forget the model of the damn keyboard. The ADB Pro keyboard or the Apple ADB 2. I forget the name of it. It doesn't matter right now. Someone's gonna. The actually police will look it up for me. The Westlife, I'm counting on you to look it up and tell me what it is, because I should know this. So this is our steel backing plate. You can see there's actually some corrosion here. Look at that. There's a little bit of corrosion. So there had been some liquid exposure at some point in this keyboard's life. Something had spilled into it. Although, yeah, I see where the rust was. But I don't see any liquid damage. I didn't wash the inside of this. I don't see any liquid damage. Okay, so once you remove the metal pan underneath, you're left with what looks like a road map on printed plastic. So let me tell you how these are made. I worked in 2 different companies. I was originally a printer. I ran a flexographic printing press, and at one point I ran a rotogravure printing press. I've run an offset printing press, and I left the industry because the chemicals and the inks and all the mess and lifting, and it was just it was a terrible job. It was a terrible job. I didn't want to do it. It didn't pay well enough, and the career, the projected career path I was headed into was looking pretty bad, bleak even. And it turns out my predictions were right. This was 13 years ago. Nevertheless, so I know how these are made. I also worked for a company that manufactured flex circuits, and my job was I worked in the planning department. It was a data entry job, but I had to build spreadsheets and work through company back-end software to determine where jobs were in the production process for big multinational corporations. So I had to go through and see what jobs were delayed and why. And when they were delayed, I had to go into the manufacturing facility and talk to the people who were actually making the product and ask them why they didn't do their job. It was a job that I did not like, so I left. But anyway, it was an interesting job working in a planning department for a manufacturing company that made these. So I know intimately how they're made. I never actually made one, but I've seen the machines, I've watched them do their jobs, and I've, so it was an interesting part of my life that I try to forget about. But anyway, so we're going to pull this up. There's actually three layers, of plastic here. The top layer is our base conductive layer. Now this layer here has another layer attached to it. Well, it's just sort of sitting there. It's clung to it. This right here is an insulating layer. So, alright, so let's talk about this one right here. Now this right here, I keep saying right here, this started out life as far as I can tell, a clear sheet of Mylar. A clear sheet of Mylar. That's how it began life. It went through another machine that die cut it into the shape you see. Actually, here's how it went down. It came off the roll. It went through a process that basically silk screens the printed circuitry that you see here. Then, yeah, I'm trying to remember if this is correct or not. So it was printed, the circuitry that you see here was printed on using a conductive ink. Then it went through a process called the die cutting stage, where they die cut this into the shape you see it. They punched in all the holes. And then went through another process that added this piece of insulating. This is actually a foam that's used to apply pressure. It's designed to force these little conducting fingers against the circuit board that it interfaces with. And that's basically how it was made. Now there's another process made where they start out with a sheet of Mylar that's metallized, like a Mylar balloon. And what they then do is they print the circuitry using a resist type ink, which is basically a masking. Think of it as masking tape. They print all that on, and then it goes through a process that washes away, using a caustic soda solution, all the metallized film that is not printed over. And I believe there's another process that removes the photoresist from the remaining circuitry that's left behind in that process. It's kind of surreal watching metal get dissolved instantly by a caustic solution. I've seen that happen. The building smelled kind of like the saltiest chicken noodle soup you've ever smelled. That's what it smelled like. It was a very caustic, very savory almost aroma. But looking at this sheet here, I think I see why this thing failed. So there appears to be residue of some kind of a liquid here that doesn't belong there. And that residue may have corroded some of the metallized ink or whatever the hell, if it's, yeah, so I'm seeing possible damage to those little tracers, and I'm going to find out if they're still conductive using an ordinary multimeter. Let's do that. Let's take a look though on the other side. Now this one went through another process, so it was made just like this one over here. But this one went through a second or third or fourth or 10th process that added nipples. It's called the nippling stage. No, it's not. I made that up. But these are added by machine in precise locations and secured with what appears to be an adhesive solution. And I'm looking at this one, and it doesn't look to be nearly as badly damaged, but I see over here possible residue from liquid. What I'm going to do is I'm going to grab my multimeter, and we're going to see if this stuff is still conductive from end to end. And that would explain why it doesn't work properly. I want to show you another thing I did. So here's the, over here we have the interface board. And it has these conductive fingers that basically touch those printed contacts. And that is how the conduction is made. Over time, and why a lot of these stop working as they get older, is plastic begins to deform in some cases, or, you know, materials degrade. Stuff happens. And this little pad here that's mounted to the back of this piece of Mylar, it begins to lose its it loses its bounce. It flattens. It relaxes in its current state. And when that happens, these little fingers stop conducting against this board. And when that happens, you start to lose parts of the keyboard, entire sections even. It's bad. Now, this keyboard definitely suffered from that to an extent because most of the keys didn't work when I got it. So what I did is I took a piece of, this is actually, here, check this out. You guys think I'm crazy now? We'll wait till you can see this. This stuff here doesn't burn. What we have here is furnace gasket material. And it has a real, apparently it does burn to an extent. It's actually burning like a match. Hold on. Oh, it went out. Yay. Okay, so it smells awful when you burn it, but this right here has a nice, this is what I have in the house. Alright, so don't judge me. This stuff here, it has nice bounce to it. It has a really nice pad-like property. And this just happens to be in my house because I had used it to fix my old furnace temporarily. And I had a whole bunch of it left over, but now I got to cut a new piece because I can't use this again. This is actually it's fire-resistant material. It has nice bounce to it. It's just the right thickness. And I added it underneath that circuit board to provide more pressure so that it doesn't lose contact with. And it did fix it. It fixed parts of the keyboard that weren't working before. Hold on a second. I'll be right back. And I'm back. So what I got here is an ordinary old multimeter. We're going to do some diagnosis work. Diagnoses. We're going to find out what the hell is wrong here. I'm going to take this layer. This looks kind of suspect. I'm going to test for conductivity in some key areas. Can you see what I'm doing? Not really. Let's zoom in over here. I'm going to look at, so first of all, okay, we're going to trace this out to here. Aha! There we go. This little tracer here is no damn good. Up to here. Right here, it's out. Look at that. Nothing. Let me see if I can zoom that in a little more. So we've identified the problem. This is why the power switch doesn't work, at least. Okay, check this out. So here's the pad that the key strikes. And over here is just a little bit ways away from it. And there's good. Oh, nothing. Nothing. Obviously nothing here. that's bad, because over here we've got one that looks pretty healthy, and it should conduct all the way to here. Nothing. Not a thing. Oh wait, I'm looking at the wrong one. There we go. Good, 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 good. Okay. Check that out. Well, how about over here? This one traces all the way around. Nothing. What about resistance? Let's set it to resistance and see. Nothing. It's open circuit. No, it's not. Not completely. But nothing here. Oh, wait a minute. I'm lying. It's 56.2 ohms. Kiloohms. Oh, wow. How about this one? Yeah, this one's definitely open. No, 115 kiloohms. So, that's not good. So it's not completely open, but it's also not where it needs to be. Can we fix it? Well, I'm not Bob the Builder, but if I had some conductive ink, I could retrace some of these and make them great again. But you'll notice that some of the healthier looking ones, you know, they're nice and healthy. See? So when it gets below a certain threshold, the meter doesn't see it. But just for funsies, let's see what it should be. So I'm going to start over here. Over at this point, I've got 2.2 ohms. Over here, 6.8 ohms. So you're going to get resistance anyway, but it's not going to be like we were seeing with the. I mean, from this point to this point, it's only like an inch, and we're getting all of. It's still open. Come on, 116K. That's no good. So all right. So that's why this keyboard's done. Done with a capital done. It's not because of any other mysterious cause. It is dead. And it looks like the damage is concentrated to this area. Most of it is right in the connector block area. And then a lot of it is around the fringes. What causes this shit? Well, moisture. Moisture causes this. If the keyboard is stored in a damp location for an extended period of time, what happens to metal when it gets wet? It corrodes, and that's exactly what's happening. This metal is corroding. What can we do about it? Nothing. Spay and neuter your pets. That'll solve everything. But otherwise, we need to replace the keyboard. Hopefully the new one that I get, the replacement one, is hopefully it's in better shape. Now this one we already know without a shadow of a doubt what we're going to find here. But because we're here, because you're watching, let's do it. Let's do it up. Alright. So between here and here, we should have a closed circuit, but we don't. We have, let's see. We have 4.9 ohms, so this might actually tone out. It does. But all the way to here, still good, still good, still good, good. And it rings around the rosy there. And it's open. So where does it stop? We're good here. Maybe we can figure out where the threshold for pain is for this meter. Good, 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 good. Good. No good. No good. So the threshold for pain, so it beeps out at 42.2 ohms over here. 45. The number should be getting higher and higher, but over here, because as resistance increases, the resistance, yeah. Got it? Alright, good. So we don't get a tone over here. 53.8 ohms. When it hits infinite resistance, that's when it obviously tones up. But as the resistance increases, 55.5. Looks like the threshold is around 50 ohms. 55.7. So at 55 ohms or so, 59. It's not open. All the way over here, it's at 70. Is that K ohms or ohms? That's ohms. All the way around the mulberry bush to the contact point at the board, it is... Did I say... Oops, I thought I saw something crazy. 82 ohms. Wow. Well, anyway. So all it's really looking for, I think, I mean, for minimal contact, it's probably looking for something like... Hell, because those keys all work. So maybe 100 ohms, maybe. I mean, if it sees that, it's not obviously looking for an open-closed circuit. It's looking for something that triggers. So there's a threshold for the triggering of these keys, and I don't know what that number is. But there's a threshold for that. So up to like maybe 50, 60, maybe 100 ohms. Anything above that, you know, like 1 kiloohm, probably not going to register. Because we know that the power key doesn't work, and we're only getting something like, what did I say? It was, it wasn't really, it was a lot of resistance. It was 117 kiloohms. So that's ridiculous. That's ridiculous. Alright. That's it for our video here. Should be getting a new keyboard soon. Hopefully soon. So I can put that Snow White keyboard with the Apple II GS where it belongs. And, you know, I might end up just buying one of the older ADB keyboards that properly would have shipped with this Mac, if I can find one at a reasonable price. That concludes our broadcast day. Not really. In the meantime, I'm going to salvage what's left here, except for the Mylar bits, and going to rebuild the keyboard that comes. But I'm going to test it first. We're going to make sure it all works out. And I'm not going to bother filming any of that because it's not really, there's no point to it. But I'm going to keep this aside. When that new one arrives, then there you go. We'll have it all done.